Okay, so we begin part 2 of circuits, and we actually are going to start drawing circuits now. So first of all, I'd like for you to get a sense of how circuit diagrams look. They can get awful super complicated if you look at them for really sophisticated devices, but we start with the basics. The basics are that circuit diagrams have circuit elements in them. Now, we've already looked at one of the circuit elements, a couple of them. One of the circuit elements is the battery. And we already know that the battery consists of a positive electrode and a negative electrode. So in circuit diagram mode, we would draw our battery something like this. There's a long line on one side and a short line on the other, and the long line always represents the positive side. The short side always represents the negative side. Okay, now sometimes you're going to see them written like this as well. But as you'll see in a bit, that's a little bit confusing with some of our other circuit elements. Another one that we've already seen is the resistor. And a resistor in real life and in your kit looks like this. But in actuality, anything that you put in your circuit outside the battery is going to provide some resistance. Now that symbol is a pretty intuitive one. It is like a rocky obstacle, right? Okay, another thing that we've looked at is the capacitor, and so we'll be looking at a few of those in our circuits as well. So you're familiar with the capacitor, and you know that also in real life they might look something like this, or a lot of times they look like all kinds of things actually. There's lots of different ways the capacitors can look in circuits. So, but in the circuit diagram itself, there are basically two ways that this is drawn. One of them is like so, where the positive side is straight and the negative side is curved. This is actually a little bit more common for the types of capacitors that you have in your kit, or electrolytic capacitors. But I like to use this way to write capacitors because the other way to write it is this. And hopefully now you can see what I mean by the possible confusion between the battery and the capacitor. Now, the two lines should be the same length on a capacitor and should not be the same length on the battery, but to avoid confusion, I prefer to use these two so that you're always clear what I'm saying in my circuit. Okay. One of the tricks to analyzing circuits is being able to translate from a physical situation to a circuit diagram situation, and vice versa. So if we take our 9-volt battery and we attach it to a resistor, and by the way, I don't recommend just attaching it to a low value resistor. We will be using 9-volt batteries, but we'll be doing it in a way where it's a little bit easier to make sure that you're not burning out your resistor. So in this case, we'll use something like your 1000 ohm resistor that you have in your circuit. If we were to use a 10 ohm resistor, then you would very quickly see something that looks like this, because you'd burn it out. Okay, so it doesn't take much. These things are a little bit fragile, right? In any case, this is our real situation, and if we were to put this in circuit diagram form, well, in circuit diagram world, we don't have to worry about things burning out or any of the physical complications like how hard it is to attach the wires or any of that stuff. Essentially what we do is we say, well, I know that a positive terminal here has been attached to my resistor right here, and that a negative terminal has been attached to the other side of my resistor, and so I would draw that in this form. And that allows me to see that the positive side is on one side, the negative side is on the other. I know where they are. Now with a resistor, it doesn't really matter which side you put it on, but for some devices it does. You certainly don't want to put the positive side on the wrong side of a particular type of motor. I think the motors that you have will still run fine with, I think all of the motors that I gave you should run fine in reverse polarity, but you never know, right? And so it's always a good idea to keep things in the right order. Your capacitors, for instance, have to be put in the correct order because I gave you the kind that are polar. So you would need to make sure that you attach the positive side to the positive side in that case, right? Likewise, if you wanted to attach two batteries in a row, you certainly would not want to do it where they're facing each other. You would want them to be, stacked in line, single file. So, all right, let's detach our battery from that particular circuit and instead try attaching something else. Like, for instance, we could apply a motor. So we could attach here. Okay, so attach a motor, and then on the other side, maybe use your alligator clips to attach a resistor. And then we would have to make sure that we were keeping this in order on our circuit. So here's one of the things that's, I think, going to be very difficult for people to get on these circuits. One standard way to write this circuit would be like this, where that represents a motor element to your circuit, and then of course we would have a resistor element to the circuit. But there is nothing about this sort of standard way of writing it that prevents us from writing it in a different way. For instance, this circuit is equivalent, even though it looks super weird, right? But the important part here is that we take the positive terminal and we go in the direction where current goes in the direction from the positive terminal on a journey through the circuit elements as they're laid out in our circuit and back to the negative terminal, and it keeps going. So we would always have current flowing like so. Okay. An important feature of your circuit diagrams are going to be taking a look at what we call nodes, or the segments of wire that exist in between your circuit elements. Okay, so we'll have one segment of wire here, and then so electrons or charge is perfectly free to move anywhere along this line. It can go back or forward. It doesn't care, right? Wherever it wants to go, it's free. It doesn't have to work hard to get from one place to the other because there's not really any resistance in there. It does have to work to get from one side of the motor to the other, and that's actually what drives the motor. You're taking electrical energy and using it to provide energy for your motor, right? Okay, so this allows us to get from one side of the motor to the other to the next segment, and this next segment, perhaps I'll put it as orange. This next segment then, charge is also free to move anywhere it wants to in that section. If it wants to go back across the motor, it's going to have an awful time doing that because that's not how our circuit's set up. But it can move to the other side of the resistor. Positive charge will flow that direction, but it has to push its way through, right? And so we like to look at these circuit segments in between the elements as very important things that will help you to analyze your circuit. Okay. Let's try that with a different type of circuit setup. So in this circuit setup, I have a little bit of a complicated looking array of elements. Here I have a bulb, and we can go ahead and add the bulb to our list. The bulb has a electrode here on the metal screw part, and then another electrode, a little dot on the end. And a lot of times is simply drawn like this in a diagram. So let's draw our diagram to represent this. We can pretty compactly create a circuit diagram for this. Now, it's not important where we place the battery. As a matter of fact, we could go ahead and place it on top, even though in our other diagram it's on bottom. So let's go ahead and do that. So here we have the positive is on the left and the negative's on the right, and that means that we have to make sure to connect the elements in order, right? So we have one resistor that is attached to our positive terminal of our battery, and then we have also, you can see here, that another is connected directly to the positive terminal of the battery. And one easy way to keep track of this is to look at that node or that circuit segment where we have nothing but wire in here, right? All the way up to these two resistors. We can even label them resistor 1 and resistor 2 and then write them accordingly in our circuit. Now, we have options at this point. We know that after we pass resistor 1, we actually are going to come in contact with the bulb. So we could put our bulb here. We could write resistor 2 here, right, to come back in contact before it reaches the bulb. Or, if we wanted to, we could actually put it on the other side. There's nothing wrong with that. So I'm going to go ahead and do that. And then we put our bulb. The important thing here is to ensure that the color code works, to ensure that the wires are connected in the correct order, to ensure that current would flow in the direction that it wouldn't actually flow in the physical circuit. So here we can look at our segments here and say, okay, there is one segment, there is another segment, and there's the final segment, and then you have to ask yourself, do these segments look exactly how they would in the physical circumstance? In other words, if you're a charge, can you freely access the positive terminal of the battery, R1 and R2 on one side? Okay, that's how we have it. Positive terminal of the battery, R1 and R2, right? Then we check the orange section and ask the same question. Can I access one side of the motor, one side of R1, and one side of R2? Excuse me, the bulb, not the motor. Yes, I can access one side of the bulb, one side of the R2, and one side of R1 in the same way that I can in this circuit, right? Great. And then on the other side of our bulb, the only things that you have access to within this segment are the negative terminal of the battery and the other side of the bulb. And that is true in our physical circuit as well. So that's how you ensure that your circuit diagram matches your physical situation. You can also go in reverse, and you'll need to in your lab, because I'll write these physical circuit or these diagrams, and then you have to create the physical circuits based on that. One last note before I go on to the next video. Each of these colors is not just a theoretical color, it actually represents something important. Voltage. We know, since this is an, let's say, 9-volt battery, that the red then, touching the positive terminal, represents 9 volts, or whatever that terminal happens to be, right? If it's a perfect battery, and it's exactly a 9.0 volt battery, you would expect, if it's a perfect battery, you would expect then this red to be exactly 9.0 volts. In section 3 we'll talk about not the imperfection of batteries, but if it's a perfect battery, then it should be fine. Now if we have orange here, that means that you have dropped from 9 volts down to a different voltage in the orange segment. So all through red here in our diagram we have 9 volts, and then we would have some other voltage here in the orange. What voltage? That's a good question. We need to learn how to analyze our circuits in order to be able to determine that, which we will begin to do in the next video. But some voltage, right? And then, of course, we know that this one is going to be 0 volts with respect to the ground terminal, because it is the ground terminal, right? So we have two ways to talk about that voltage. You can either say this is 9 volts with respect to the ground terminal, and the orange one is, let's say, 6 volts, right? And then if the orange is at 6 volts, then that means that we're saying 6 volts with respect to the ground terminal of the battery. That's one way to talk about that orange section. Another way to talk about that orange section is called voltage drop. So if we went from 9 volts on one side of our resistors to 6 volts, that means that we lost 3 volts, right? So we had a 3 volt drop. It is okay to say voltage drop. It is okay to say difference in voltage. It is okay to say voltage across. But voltage through is a terrible way to talk about voltage, because it's a misnomer. Voltage doesn't go anywhere, right? And so it's not helpful to talk about it in terms of its motion. It doesn't. We either shed voltage, lose voltage, drop voltage, or we have voltage differences, right? So we have a 3 volt drop in that case from red to orange, and then we would have an additional 6 volt drop from orange to black. Okay. We'll continue that process and talk about the two basic types of circuits in the next video.